Good day, Miss Labor. Good day, everyone. Our topic is about the conceptual systems design, which is the third phase in the systems development life cycle. To review, the systems development life cycle is a conceptual model used in project management that describes the stages involved in an information system development project from an initial feasibility study through maintenance of the completed application. SDLC is used to give a rigid structure and framework to define the phases and steps involved in the development of a system. I am Julie CHATTO, and I will be the one to give you an overview about our topic. Our report consists of the introduction to conceptual design, the structure design and object-oriented approach, and the role of auditors in the conceptual systems design of the system development life cycle. The third phase specifies in detail the specifications, features, and activities required to meet the functional requirements of the proposed system that will be implemented. The design phase can also be referred to as a transformation phase because it is when an idea is actually transformed into a real working system. Design phase begins when a customer signs off on allowing the team to start building and creating. This is the stage at which end users debate and decide on their unique business information requirements for the proposed system. During this phase, they will think about the system's key components such as the hardware and/or the software, structure or network capabilities, processing, and processes. For now, let's watch a video that will help us understand the conceptual systems design from another perspective.
We start by concentrating on the business or organisational needs and what the resultant requirements for the eventual solution might be. Business needs and requirements are, after all, what we are trying to address, so understanding these is a logical starting point. We then have a look at what the relevant stakeholders within the business would like to achieve. These stakeholders will be people who are involved with the business or the organisation in areas where the need exists. They will have particular views on what's required by the eventual solution. The stakeholders I'm talking about here are people who have a right to influence the requirements of our system. This simple definition might help you when you're trying to identify the stakeholders. We then move on to what some people consider to be the start of traditional systems engineering, where we take the business and stakeholder needs and develop a formal understanding of the system-level requirements that our potential solution must meet if it is to satisfy the stakeholder and business needs. An understanding of the system-level requirements allows us to take a detailed look at the potential system-level solutions that might exist. We'll be interested in knowing what the level of compliance these solutions will exhibit, what options the solutions will come with, how much they will cost and how long they will take to realise. We will also be interested in the risks associated with each solution and the longer-term issues such as sustainment and disposal. This will allow us to select a preferred system-level solution. This is a process that's sometimes referred to as system-level synthesis to give the feeling of evolving design. The term synthesis has its roots in Latin and before that Greek, meaning to place together. The need to stop our work periodically and check that we're in the right place is almost so obvious that it goes without mention, but in this MOOC, we'll mention it anyway. Once we've done all this work with our business stakeholders and we think we're ready to move on to solving their business needs, we will draw some breath and have a bit of a look at what we've achieved. This gives everyone a chance to review the work, look at the problem space that we've defined, look at the preferred system-level solution we've selected, and confirm that we are ready to move on to the next stage. We call this review a system design review because that's what it is, a review of the system-level requirements and the system-level solution to ensure that the two are appropriately understood and appropriately matched before proceeding.
The main focus of this phase is to determine how data will flow and be stored. and its goal is to generate various different conceptual systems that meet the system requirements discovered during systems analysis. The systems professional avoids putting preconceived limits on the new system by offering consumers with a range of realistic choices. The user will analyze these conceptual models and choose the options that appear to be the most realistic and attractive. The design phase comes to an end, just like how it begins, when the customer signs off. The conceptual system that develops advances to the SDLC's final phases when it is detailed developed and executed. The structured approach and the object-oriented approach to conceptual systems design are described in this phase. The structured design approach creates each new system from the ground up, while the object-oriented design approach constructs systems from the ground up by assembling reusable modules rather than creating each system from start. Object-oriented design is most commonly linked with the iterative approach to SDLC, in which tiny chunks or module cycles through all of the SDLC phases quickly, with a short time frame from start to finish. Then, in some proper order, further modules are added until the entire system has been constructed. Our report focuses on the two conceptual design approaches, which are the structured design approach and the object-oriented design approach. The structured design approach is a methodical technique to creating systems from the ground up. It entails beginning with a broad picture of the proposed system and subsequently decomposing it into more and more detail until it is completely understood. It is a method involves a step-by-step approach to a system building process, logically moving from one developmental phase to the next. While in the object-oriented design approach, its goal is to build information systems from reusable standard components or objects. This approach may be equated to the process of building an automobile. Car manufacturers do not create each new model from scratch. New models are actually built from standard components that also go into other models. In the object-oriented approach, the focus is on capturing the structure and behavior of information systems into small modules that combines both data and process. The main aim of the object-oriented design approach is to improve the quality and productivity of system analysis and design by making it more usable. That would be all for the overview of the conceptual systems design. My groupmates will tackle in detail the structure design, object-oriented design, and the auditor's role in conceptual systems design. Thank you.
Good day, everyone. I am REIZA DARATO, and I will continue to discuss the Conceptual System Design Phase 3. The Structured Design Approach. Figure 5.4, which is the top-down decomposition of the structured design approach. Before that, what is top-down design approach? Top-down design approach is an approach starts by identifying, or we try to figure it out, what are the major problems of the components of the software system. As we figure it out, we try to decompose them into lower level components, and we repeat this process again and again until the desired level of detail is achieved. It is suitable only if the specifications of the system are clearly known and development is from scratch. This approach is a reasonable approach if a waterfall type of process model is used. What do you mean by waterfall type? This means that this take task and subdivided into subtasks from the top to bottom, that which eventually end up with small enough function that can be easily programmed. This approach creates solution for the main problem. As you can see on figure 5.4, the top-down decomposition of the structure design approach. This is how the system designer follows top-down approach. From the context level DFD process 2.0 is decomposed into intermediate level DFD, and then the intermediate level DFD process 2.3 is decomposed into elementary level DFD. The decomposition could involve several levels to obtain sufficient details. Let's just assume that it has only 3 levels. That is sufficient in this case. So, the final steps transform process 2.3.3 into a structured diagram that defines modules that will constitute the process. So why decompose? To split up into function, which is easy to code, easy to test, easy to reuse, easy to assign people to the specific task because they have specialties. So I'm going to show you a video.
So first of all, it's easy to write and test the program because when I got small functions, okay, they're shorter, which means they're easier to write, and they're also easy to test and debug. Alright? It's easy to see the relationship between different functions in this top-down design. Okay? So they're not interference between different functionality on my phone. As each function is written, it can then be you can do integration testing to make sure that 2 different functions work together without interfering with each other. It's easy to manage your team members because you can assign multiple people to the same task. Okay, you can also put people on specific tasks. So for example, on that previous slide, that guy Jim might have a specialism in digital to audio, whatever it is, conversion, right? So I might assign him those functions to program on the receiving data, and we're converting from digital to analog or analog to digital, right? And then when it's to do interface design, I might assign a different member of staff because they've got different specialisms. Okay. It's also, you can identify reusability, like I talked about the vibrate function being used across several different things. Well, why am I getting the people working on the text messaging app and on the keyboard and on the thing all to write a vibrate function? Someone just needs to write one, which can then be reused by many different people. Okay, so your code base becomes smaller and you're less likely to have bugs, and it also makes it easy to update in the future because you're only updating one part of your code base, not the whole thing. Alright, other reasons for using top down is you're breaking the problem down into functional components. Okay, so it's easy for you to see what needs to be done where. Right, this kind of approach was popularized really in the 1970s. Okay, because this is how this is a really kind of hierarchical, top-down structured way of seeing things. Top-down design doesn't have to be hierarchical. You can also think about parallel processes because things don't often happen one after the other in a sequence. Often in modern applications, we're making use of multiple threads. All right, so you can use top-down design to think about that parallel approach. You can also, instead of thinking about hierarchies and processes, you can think about data flows. Okay, so you can actually map out where the data is moving around the system, where it's being stored, and where it's being used. Okay, that will also then help you to identify what might be going on within your program. Problems with top-down design though is this assumption that you know the whole solution in the beginning, right? And this is linked to the problems with top-down hierarchical approaches like the waterfall solution or the waterfall method, which, you've done your analysis, so therefore you've got the requirements, therefore you do your design, and so on and so forth, okay? And we know that in the real world, okay, things don't work like that. Plans change, ideas change, okay? The market might change, and so your software needs to adapt in order to be successful. Event-driven programming also is another paradigm, okay, a way of programming, and top-down design doesn't really work well with event-driven programming because you're not really breaking down functions, you're thinking about what actions need to take place when a particular event is triggered.
Next is the figure 5.5, Alternative Conceptual Designs for a Purchasing System. As you can see in figure 5.5, it has two alternative conceptual designs for a purchasing system. Option A, batch system, and the option B, ADI system. Though this system lacked the details needed to implement the system, for instance, not including the database record structure, processing details, specific control techniques, formats for input screens and source documents, and output report formats. However, this design possesses sufficient detail to demonstrate how the two systems are conceptually different in their functions. Option A is a traditional batch purchasing system in which the initial input for process is the purchase requisition from inventory control. When inventories reach their predetermined reorder points, new inventories are ordered according to their economic ordered quantity. Transmittal of purchase orders to suppliers or the vendors takes place once a day via the U.S. mail. In contrast, option B employs EDI technology. The trigger to this system is a purchase requisition from production planning. The purchase system of option B determines the quantity and the vendor, and then transmits the order online via EDI software to the vendor. Both alternatives have pros and cons. A benefit of option A is its simplicity of design, ease of implementation, and lower demand for system resources than option B. The negative aspect of option A is that it requires the firm to carry inventories, while option B allows the firm to reduce or even eliminate inventories. The benefit comes at the cost of more expensive and sophisticated system resources. At this point, system designers are concerned only with identifying plausible system designs. And that ends my report.
So, hi guys, my name is HANDEL BULLECER. So, I will be tackling about the structure design approach. So, before anything else, I would like to do some short recap about what have the previous reporters have discussed. So, according to the reporters, we have learned that there are two approaches to conceptual systems design. The first one is the structured approach, and the second one is called the object-oriented approach. The first one, the structured approach, develops each new system from scratch from the top down. And on the other hand, the object-oriented design, or the OOD, builds systems from the bottom up through the assembly of reusable modules rather than create each system from scratch. So in my report, we will focus more on the structure design approach. So the structure design approach, it is a disciplined way of systems from the top down. The business process under design is usually documented by data flow and structure diagrams. This design approach consists of starting with the big picture of the proposed system that is gradually decomposed into more and more detail until it is fully understood. And also, under this approach, the business process under design is usually documented by data flow and structure diagrams. So there is a figure 5.4 which shows the use of data flows diagrams or DFDs and a structure diagram. It is to depict the top-down decomposition of a hypothetical business process. So this is the figure 5.4 top-down decomposition of the structured design approach. So we can see here the first is the data, and then it goes down to the process. Before the process is the input, and it goes to the process, another process again, and then the output. And it is called the context level data flow diagram. The lower part is the intermediate level data flow diagram. The third one is the elementary level data flow diagram. We can learn in this figure that the structure design approach is really from top down, because it shows in the figure that the first one is from the top and then it goes to the bottom until you finally reach the output. Mm. Next is the conceptual design phase. The conceptual design phase should highlight the differences between the critical features of competing systems rather than their similarities. The designs should identify all the inputs, outputs, processes, and special features necessary to distinguish one alternative from another. So, therefore, system designs at this point should be general. The designs should identify all the inputs, outputs, processes, and special features necessary to distinguish one alternative from the another. Again, I will show you the figure. There is a figure 5.5 which presents two alternative conceptual designs for a purchasing system. However, these designs lack the details needed to implement the systems. So for instance, they do not include these necessary components. The first one is the database record structures. The second one is the processing details. The third one is the specific control techniques. The fourth is the formats for input screens and source documents. And lastly is the output report formats. However, these designs do possess sufficient detail to demonstrate how the two systems are conceptually different from their functions. And lastly, here is the list of differences of the two approaches of conceptual design, system design making. So as we can see here, the structured approach, it works on top-down approach, which I said earlier. The DFD is starting from the top and going to the bottom. Program is divided into number of submodules or functions. Function call is used. Software reuse is not possible. Structure design programming usually left until end phases. Structure design is more suitable for offshoring. It shows clear transition from design to implementation. It is suitable for real-time system, embedded system, and projects where objects are not most useful level of abstraction. Data flow diagram or DFD and entity relationship model the data. And lastly, in these projects can be managed easily due to clearly identifiable phases. The next is the object-oriented approach. So object-oriented approach works with bottom-up approach, which is very different from the structured approach. The second is program is organized by having number of classes and objects. Third is message passing is used. Next is reusability is possible. And then object-oriented design programming done concurrently with other phases. Next is it is suitable for in-house development. Not so clear transition from design to implementation. Next is it is suitable for most businesses applications game development projects which are expected to customize or extended. Next is class diagram, sequence diagram, state diagrams contribute. And then in this approach, projects can be difficult to manage, especially in the transition between phase.
Hi everyone, I am January and BETE, and for now I am going to discuss the object-oriented design approach. Object-oriented design or OOD approach builds information systems from reusable standard components or objects. It is focused on capturing the structure and behavior of information systems into small modules that combines both data and process. The main aim of object-oriented design is to improve the quality and productivity of system analysis and design by making it more usable. So, in analysis phase, object-oriented models are used to fill the gap between problem and solution. It performs well in situations where systems are undergoing continuous design, adoption, and maintenance. It also identifies the objects in problem domain, classifying them in terms of data and behavior. So, to further understand the object-oriented design, the simplest way to explain object-oriented approach is to use something like a car as an example. Like, as we all know, a car has a model name, a color, a year which it was manufactured, an engine size, and so on. So what we will do is to create a car as an object with the name, color, engine size, and year as the attributes. So for every new car we use, we would use the car object. For instance, we can have a 2019 blue BMW or a 2020 red Toyota Vios. In each instance, we would reuse the code contained in the original object. The concept of reusability is central to the object-oriented approach to system design. Once created, standard modules can be used in other systems with similar needs. Ideally, the organization's systems professionals will create a library or an inventory of modules that can be used by other system designers within the firm. There are also benefits of this approach, and this includes facilitating changes in the system at low cost, promotes the reuse of components, simplifies the problem of integrating components to configure large systems, and simplifies the design of distributed systems. There are also 4 features of object-oriented system, and this includes encapsulation, abstraction, inheritance, and polymorphism. So first, let's talk about encapsulation. An encapsulation is a process of information hiding. It is simply the combination of process and data into a single entity. Data of an object is hidden from the rest of the system and available only through the services of the class. It allows improvement or modification of methods used by objects without affecting other parts of a system. To explain this, we can use a role-playing game as an example, like Mobile Legends. So in a typical role-playing game, we may have a main character or hero, diba? And this hero will have several variables like name, outfit, hair color, and skin color. The hero may also have methods like attack, walk, run, and talk. Typically, these would be private variables and methods that can't be modified by other objects in the game. The hero may also have a variable health and a method called damage. These would typically be public variables and methods which can be modified by other objects. An enemy object would be able to call this method and change the value of the variable when it attacks the hero. Next is abstraction. So, an abstraction is a process of taking or selecting necessary method and attributes to specify the object. It focuses on essential characteristics of an object relative to perspective of user. Abstraction can also be seen as an extension of encapsulation. Oftentimes, programs are very large with thousands of lines of code. This is difficult to maintain, but abstraction helps with this. Abstraction means that every object only exposes a high-level mechanism for using it. Thus, the code within, to a large extent, becomes irrelevant to other objects interacting with the object. Using the game example, the attack method may have many lines of code contained in it. This code can specify how the hero can be attacked and what effect the attack may have on the health of the hero. The enemy object does not need to be aware how the attack works, just that it works and it reduces the health of the hero. The third feature is inheritance. Inheritance is a great feature that allows to create subclasses from an existing class by inheriting the attributes and operations of existing classes. As stated before, programs often contain thousands of lines of code, which is complicated and difficult to maintain. Another problem often encountered is that we have similar objects. They can share some code or logic, but they are not exactly the same. If we had to create a brand new object for every object we use in our program, it would lead to more code and complexity. In order to prevent this, we can use inheritance. With inheritance, we extract the logic in one object, called the parent, to another object called the child. So, in our example, the game example, we can have a variety of enemies. These enemies can all be child objects of a parent enemy object. Each enemy may have similar attributes, but also different attributes like outfit or weapon. The fourth feature is polymorphism. A polymorphism is the ability to take on many different forms. It applies to both objects and operations. A polymorphic object is one whose true type hides within a super or parent class. In polymorphic operation, the operation may be carried out differently by different classes of objects. It allows us to manipulate objects of different classes by knowing only their common properties. So, we have now seen how inheritance enables us to use a parent object to define a child object. The problem is that the child might have a different way of implementing a method. Polymorphism gives us a way to use an object exactly like its parent, but keeping its own method as they are. As an example, let's look at a vehicle object. We can use this object to create other objects like a car, a truck, or a motorcycle. If the vehicle has a start method, it may be implemented by each child object differently. Polymorphism enables each child object to implement the start method differently. Like in our game, our enemies may each have an attack method which it inherits from the parent, but each with its own implementation. That ends my report. I hope that you have learned something from me about object-oriented approach.
Good day, everyone. As a review, the SDLC, or the Systems Development Life Cycle, is an 8-phase process consisting of 2 major stages: the new systems development and the maintenance. So the first 7 phases of the SDLC describe the activities that all new systems should undergo, starting from the systems planning, systems analysis, conceptual design, system selection, detailed design, programming and testing, and implementation. New systems development involves conceptual steps that can apply to any problem-solving process, which involves identifying the problem, understanding what needs to be done, considering the alternative solutions, and selecting the best solution among those alternatives, and finally implementing the solution, which is on the seventh phase of the SDLC. So our group is going to tackle the third phase. The third phase describes in detail the necessary specifications, features, and operations that will satisfy the functional requirements of the proposed system which will be in place. This is the step for end users to discuss and determine their specific business information needs for the proposed system. It's during this phase that they will consider the essential components such as the hardware and or software structure, the networking capabilities, processing, and procedures for the system to accomplish its objectives. Again, phase 1 is the requirement collection and analysis. Phase 2 is the feasibility study. Then on the third phase is the design, which is this conceptual systems design, then coding for the next phase, from the made design, testing, installation, and lastly, the maintenance. The first question. The last part of the phase 3 is the auditor's role in conceptual systems design. There's this special participation of the auditor in making the conceptual systems design. The first question is that why are they involved? Should it be that the systems design only is for the IT's job? Is that the IT's job? But no. Auditors are involved in this phase. Why? Because they are experts in financial transaction. They are knowledgeable enough to guide what the next steps would be and how the flow of the design will go following the course of business, which is the accounting course. The purpose of a financial audit is to provide an expert opinion regarding the fair presentation of the financial statements, which is basically the auditor's job. To render such an opinion, the expert auditor must perform certain audit tests. Naturally, the accuracy of the financial data in the client's databases bears directly on the auditor's opinion. The accuracy and integrity of these programs directly affects the accuracy of the client's financial data. A materiality flawed financial application can corrupt the financial data of the system, which are recorded in the system, which are then incorrectly reported in the financial statement. So that's why auditors are involved. Next is the quality of accounting information system is determined in systems development lifecycle. As the phase goes on, the need of auditor is essential. Since it is making a system for the business will always involve accounting processes. Auditors must always be there or be the one to check whether the system plan will be aligned with the accounting principles such as the GAAP and other principles that would involve the IT system or the proposed system. Next question is that how are they involved? They are involved as first users. Since they run test controls as auditors, it is necessary that they view the system as users of it. Its purpose is to check if the system planned and designed is applicable to be used and is accessible for target users of it or the administration through accounting techniques that will also be applied. The auditor should become involved at the inception of the process to make conceptual suggestions regarding system requirements and control. That's why they are involved. That is the role of auditors as users. Next, how are they involved is that they are also members of the SDLC development team. The auditors essentially needs to minimize control risk. Why? Because like what I said, they are the one who execute control tests for the design systems, the proposed conceptual design. With this, they can help the development team or any team to identify which part of the system have errors or need changes. That's why they're also part of the SDLC development team, even though they are auditors. Auditors can be part of financial management and other teams, but in this phase, the conceptual system design, they are needed as members of the development team. They are also involved as, obviously, the auditors. Generally, it is the auditor's job to audit or examine the system and use techniques to further test its capability. Advanced audit features. There are some advanced audit features that cannot be easily added to some part of the system due to technical problems such as the programming language, example is the COBOL, which does not support ALE, or which does not support something that the audit feature will be put. Auditors should analyze what is best suited for the system. That's why they are really needed on the conceptual systems design phase. The auditor is often consulted during the systems analysis phase when security requirements for new system are determined, since there are special auditability features that needed. During the design phase, the auditor will often test controls to ensure their adequacy. The operation and maintenance phase, the last parts, lasts definitely, and it's during this phase that the auditor conducts his routine audit test or repeating or sunod-sunod na audit test to ensure its accessibility or to check if it is correct or there are some errors. If audit evidence shows that the computer application's process data is correct and accurate, the auditor can form the basis for reducing the amount of substantive testing that needs to be performed. He or she can lessen the test controls or not do it
always, since the client organization could, however, have hundreds of financially significant applications. Testing application controls can prove to be a highly technical and time-consuming activity. Auditors therefore seek efficient and effective ways to limit the application testing. But if, however, audit evidence shows that systems development lifecycle controls to be weak and inconsistently applied, application testing and substantive testing cannot be reduced. In some situations, it may even be necessary to expand the scope of the audit beyond the conceptual systems design. Generally, the auditor's objective in testing controls over these processes, over all of the processes in the phase, is to establish application integrity and thus limit the test of application controls and substantive testing that needs to be done. In conclusion, auditors' involvement should continue throughout all phases of the development process and into the last phase, which is the maintenance phase. As a recap, so that's all of the role of the auditor. As a recap of the conceptual systems design, which is the phase 3, we have here the definition. Conceptual design is the early phase of the design process. It is arguably the most critical design phase, during which the broad outlines of function and sort of something are coupled or articulated. It includes design of interactions, experiences, processes, and strategies. Its purpose, which is also discussed on the first parts or our first members, is to build a conceptual model and produce several alternatives based upon the previously identified requirements from the first two phases, phase 1 and phase 2, to generate the final model or the final systems design. It formally establishes the initial idea. Generally, its objective is to transform the requirements into complete and detailed system design specifications. This phase also describes have two approaches which have been discussed by our co-members, which is the structured approach and the object-oriented approach. The structured approach develops each new system from scratch from the top down. So top down which means from above, like this sample figure. Then the structured approach consists of starting with the big picture of the proposed system that is gradually decomposed into more and more detailed until it is fully understood. Then in the object-oriented approach, the focus is on capturing the structure and behavior of information systems into small modules that combines both data and processes. I've researched on this approach, and commonly this is how it is viewed. There are small parts which are also used and connected to each other. Its objective is to improve the quality and design by making it more usable. Analysis, implementation, and design, they are all connected with each other. And that is what we call as object-oriented, which means they are generally oriented with each other, with each part. of the design. The last part is the auditor's role. The auditor is a stakeholder in all financial systems and thus has interest in the conceptual design stage of the system, like what I've discussed. The auditability of a system depends in part on its design characteristics. Some computer auditing techniques require systems to be designed with special audit features that are integral to the system. These audit features must be specified at the conceptual design stage, and that is all about the Phase 3 conceptual systems design. Here are our co-group mates: JULLIE, CARMELLE, CHATTO, REIZA, DARATO, HANDEL, BULLECER, JANUARY, and BETE, and me, JULLIE, Basio, reporting about the Phase 3 of the SDLC, which is the Conceptual Systems Design. Thank you.